Okay, so now we are going to dig deeply into this radius anomaly equation. And as a reminder, this is the equation that we ended up with at the end of our last lesson. And it expresses the position, if this is our planet, the position of an orbiting body. So this is the body here that's following on the geodesic, right? So this is a geodesic equation, right? This is a result of our geodesic equations. We ended up with this radius anomaly equation. So presumably there's a body that's following some path in space-time, and that path is influenced by all the gravitating matter. And for right now, all the gravitating matter is spherically symmetric. So this kind of path is extremely unlikely because if we have a perfectly spherically symmetric piece of matter, we're not sure how it could possibly wind its way through space-time in anything other than a very predictable kind of simple path. But I'm just going to hypothetically say, hey, it's following through space-time on a free-fall path. And the radius anomaly equation is intended to tell us this would be the true anomaly, sort of its closest approach, the angle from its closest approach to where it is in the sky over this planet, and it has a distance. So it's the function, so it's the radial, the Schwarzschild radius is provided as a function of the true anomaly. That is the solution to this equation. So given the true anomaly, this equation should predict the Schwarzschild radial variable. Now, I'm emphasizing this wacky, curvy path, which is completely incorrect, because I want to emphasize that we're talking about orbits, but we can't be sure that we're going to be dealing with elliptical orbits, parabolic orbits, hyperbolic orbits, like we would in Newtonian mechanics, right? We're expecting these orbits to limit to those objects, but there should be something different. We all know, for example, that orbits in general relativity precess, right? That's sort of a famous fact that the perihelion of Mercury, the planet, sort of orbits like this, right? And the perihelion is always changing, and and plus, there's also another thing we expect. Black holes suck up matter, right? Black holes suck up matter. So if this was a black hole, which is spherically symmetric, or a neutron star, aren't we expecting some orbits to go kind of like this? An unbound object flies in and then goes, oops, gets sucked in. That's not possible in Newtonian mechanics. Now, in Newtonian mechanics, you could have an orbit that intersects the surface of a star, so it kind of hits the surface, but it's not sucked in. If the star was smaller in Newtonian mechanics, the object would just go around it. It would just be a very tight bend. But in general relativity and in the spherically symmetric solution of the Schwarzschild spacetime, you can literally be unbound object can actually be sucked in. Now, it's not evident that that's the case yet, but so this is a bit of foreshadowing in a sense. But the fact is, the orbits that are a result of this equation are limit to the orbits that we know about, but they are very, very different in many, many properties as well. So we got to keep that in mind as we study this. So I just drew this line a little glibly, but the point I'm trying to make is that this equation it's not the geodesic equation of rho in terms of lambda, where lambda is a parameter that somehow parameterizes this path in space-time. That is kind of where we want to be. Ultimately, we want that parameter to be the proper time. So we want rho as a function of the proper time. And the proper time is this length along the path in space-time. And keep in mind, too, when I draw this path, I'm not really drawing a path in space-time here. I'm drawing a path in space, right? Because here's the planet, and here's the path in space. The path in space-time would actually look like this, where I've now drawn the planet is stationary in space, but it's moving in time, so it creates this sort of cylinder, and the orbit is this conical, well, the spiral. I shouldn't even say conical. This would be a bound orbit, right? A bound orbit would be this spiral. That's what the space-time orbit is. So the real idea is that this length here, right, this is the path length of a segment of that bound orbit, And that path length is parameterized by lambda. However, if we choose lambda to be tau, the proper time, then this path length itself, the actual path length, is the parameter we're using, and it's an affine parameter, and ultimately we want rho of tau, which would tell us at any given point, it would tell us the distance between the center of the planet and this satellite object. And we would have a separate equation for phi of tau, which would tell us the angle between the true anomaly angle between this object and the center of the planet. And likewise, we would have an expression for theta of tau, which we already know is just going to be pi over 2, because we've established that. So that's sort of an uninteresting one. But the last one, or the first one, is the coordinate time as a function of tau. And remember, in this picture, this axis here is the coordinate time axis. This direction here, this distance here, is the proper time of the particle. That length, which is the integral, of the square root of minus g mu nu times this path x dot mu x dot nu, right? That integral d lambda, right? That's what tau is, right? Tau is that length, where lambda goes from, say, lambda 0 to lambda 1, right? Some other parameter of the path. And that is the path length. And if we use that to parameterize the curve, which is kind of weird, because in the integral we have this other parameterization, but this length is the parameter we actually will seek to use ultimately, which is the proper time. So here's the proper time, it's that length. But the coordinate time is this distance, I guess it would be the ordinate distance in this particular chart, this particular three-dimensional projection of this motion. Fortunately, we can suppress a whole dimension because we've made this, we've lost a dimension because we have this assumption that everything happens in a plane. So that's why we're able to use 3 dimensions to capture this world line. With the Kerr black hole, it won't be so easy, because the Kerr black hole, you cannot do this. Now, we'll talk about that later. That's a black hole that's rotating. So, so the point is ultimately we want these 3 equations, because the radius anomaly equation, it'll give me the shape in space of the orbit. You know, I tell you the true anomaly, it tells you the distance. And you can plot that out, and you can actually get a very precise picture of where the orbit is relative to the planet for any true anomaly, including true anomalies that are greater than 2 pi, which presumably should show the precession of the orbit. And it would be, if you had this, you might have it as an exact solution. I'm going to show you that we can get the exact solution for this, an analytical solution, right? Although there are some caveats with the concept of an analytical solution, which I'll talk about in a moment, or eventually. But the problem is there's nothing in here about time, so we don't know how fast it's moving on this orbit. All we know is the shape of the orbit, because time doesn't show up here. Coordinate time doesn't show up, nor does this. Remember, it's an ordinary differential equation, so the independent variable is phi, the true anomaly, and the dependent variable is rho, the Schwarzschild radius. So we don't have any idea how fast it moves along this curve, unless we get this guy, which tells us how quickly the coordinate time clock is changing relative to the proper time. Or we don't even need that. If we have this function, we can tell you how fast it moves according to the proper time clock of the falling particle. So if you're on the particle, we'll know exactly what clock reading you will arrive at a certain radial distance at a clock reading as long as you're on the particle, if you know this expression. Likewise, you'll know your true anomaly for a certain clock reading if you're on the falling particle. But if you're watching it from a distance or from some other position that uses the coordinate time, then that coordinate time value, you need this function, which is actually one of the harder ones to get. And we'll get all of these eventually. By the way, let me emphasize, the coordinate time might not be the ticking clock of anybody, right? In the Schwarzschild geometry, the coordinate time t is the time of a very, very distant observer. So if you're a person if you're observing this from way far away, so far away, here's your world line, right? You're just so far away that this distance, rho for you is, approximately equal to infinity, right? In that case, your proper time along this, your tau, is going to equal the coordinate time. But if you're close to this star here, your proper time, if you're suspended from the star a certain amount of distance, right? If you're very close, but you're suspended a certain distance, your proper time, tau, is not going to equal the coordinate time, right? You have to be very far away for your proper time to equal the coordinate time. So it's important to understand in general relativity, the time coordinate does not necessarily have to be the proper time of anybody. There is a coordinate system out there where it doesn't matter who you are, the coordinate time is not anybody's proper time. It's simply a coordinate to help you understand how to solve the problem. And if you really want to know this according to somebody's ticking clock, you're going to have to either go you're going to have to go into somebody's proper time frame to figure this out. But anyway, that's all for later. But for right now, I want to make sure everybody understands exactly what we're solving for with the radius anomaly equation. We're solving for something much less than our noble goal of these three expressions. Well, four, but one of them we made an assumption about. But these three expressions that are left, that's our noble final goal. But we're doing this intermediate goal of just getting the shape of the orbit, which is a totally legit goal. I mean, I'd like to know what the shape of an orbit is around a black hole. It's kind of why I embarked on this project. Okay, so we have to start working with solving this. So again, we have to start crunching these numbers a little bit, and let's begin and do that. The first thing we will talk about is, let's look at this units, right? So this is a Schwarzschild radius. We have g equals c equals 1. So we know that we're dealing with masses that are measured in centimeters, energy in centimeters, time in centimeters, distance in centimeters. This angular momentum is also going to be in units of centimeters too. So all of these things are in centimeters. So this last term here this is a distance. Alpha is a distance, because remember alpha was equal to 2m, right, in some set of units. But right now alpha is a centimeter unit. So we have centimeters and centimeters, which is centimeters squared. This is centimeters squared. This is centimeter cubed times centimeters. So that's centimeters to the fourth divided by centimeters squared. So that's centimeters squared. This is centimeters to the fourth divided by centimeter squared, which is centimeter squared. This is dimensionless. This is dimensionless. K squared is dimensionless. You may remember that when I say K, of course I mean kappa. Kappa was the constant of the motion that was dt d tau 1 minus alpha over rho, right? So that's dimensionless. And therefore this is numerator's dimensionless, so that's squared. And then this, of course, angles are dimensionless, and the numerator here is rho, and the whole thing is squared, so it's distance squared. So the units are good. All right, so step one of this thing is to make it dimensionless. Dimensionless. We already talked about how rho has dimensions of length, so we got to get rid of that. The reason is we're trying to turn this into a purely mathematical object that we can attack using mathematical tools. And mathematics, it's written in in terms of functions of an independent and dependent variable, right? And those functions, when they're described arbitrarily, they are unitless, right? X doesn't have units when you write down some crazy function like this quadratic function here. So we want all of our expressions, if we're going to start attacking this mathematically, the first step is to make it dimensionless. When I talk about something being dimensionless, what I mean is that the independent variable and the dependent variable have no dimensions. Right now, our independent variable has dimensions of length, so we got to get rid of that. So how do we get rid of the dimension of length? Well, the way we do it is we look for the only length scale of the problem, and the length scale of the problem is alpha. Alpha is a length scale that it's the only defining length scale of the problem. And as I told you before, it actually equals 2m ultimately in units when g is in alternative units, it would be 2 times the mass. But here, if g equals c equals 1, it's 2m, where mass is measured in length. But the point is when mass is measured in length, like we are doing, alpha is a length of the problem. So alpha is our only length. So the only way we can really make this thing dimensionless is to redefine a new variable, I'll call rho star, which equals the current independent variable, or the current dependent variable rho, divided by alpha. And I'm going to make that substitution everywhere. So everywhere I see a rho, I want to place it with a rho star, which means everywhere I see a rho, I need to multiply by alpha and then replace the rho by a rho star, because rho is going to equal alpha rho star. Seems trivial, but it's an important thing to do. Okay, and here it is with that substitution. This substitution pulls an alpha squared, which is just a constant, comes right out of the derivative, but it's squared. Here, this rho to the fourth brings me an alpha to the fourth here, and alpha to the fourth appears here. This one gets an alpha squared, this one gets an alpha squared. Then I divide through by alpha squared, so I only have the derivative of rho star, and this fourth will become a 2, this 4 will become a 2, that'll go away, and that'll go away. That'll become a squared, those will go away, and this one will go away. And so this is the next phase of our process. Now notice we don't have to do the same for phi. We don't have to make that unitless because it's an angle. It already is dimensionless. So now our dependent and independent variables are dimensionless. And all the dimensionality is housed in this thing. But notice that's a length, and that's a length. So that's actually unitless, and that's unitless, so this guy's unitless, and the same thing here, that's unitless. So actually, every single term here is unitless, and of course it has to be because this guy here is unitless. Now, that's unitless and that unitless, so there's no units on the left, so clearly there's no units on the right, and everything seems to be okay. So now it's worth refreshing ourselves about this kappa here. Remember, kappa was a constant of motion derived from this expression. The ratio of the rate of change of the coordinate time with the proper time times this factor, 1 minus alpha over rho, equaled kappa, which we said was unitless. How do we interpret kappa? Well, imagine rho is really, really large, right? And this term goes away. So this term becomes, well, it becomes 1, right? Equals 1. Then we can write this expression. dt is kappa d tau. But we know from special relativity, an expressions like that from special relativity, which I assume you have some familiarity with. Matter of fact, you better have a pretty strong familiarity with special relativity if you're in this class. But the point is that if rho is really, really, really large, we expect all the effects of gravity to be gone. If you're a spherically symmetric gravitational system and you're far, far, far away from the center of symmetry, then unless you have some weird system where the mass is spherically symmetric throughout all of space-time, kind of periodically in shells, in say concentric shells or something, we're expecting that the effects of gravity should disappear for very, very large distances. So we're assuming that that's the case here, right? There's no bizarre arrangement of matter that still has gravitational effects at infinity. So if you have that, then this should reduce to the special relativity rule, which is dt equals gamma d tau, where gamma is that famous gamma factor. And we know that that gamma factor can be understood as the total energy, which is over the rest energy. It's the fraction of the total relativistic energy over the rest energy. So that's what you can understand kappa to be. Kappa is something very similar to the total energy over the rest energy. The difference is that kappa has this term in here, which subtracts a chunk out because presumably when you get negative energy for being inside a gravitational well. So that makes some sense even from our Newtonian intuition. In fact, it's entirely informed by our Newtonian intuition that being inside a well would be counted as negative energy. So it sort of chips away at this ratio. Anyway, so that's what the kappa is all about. The h, I think it goes without saying, if you go back to its constant of the motion, it's essentially the angular momentum. But the units are going to be essentially the angular momentum per unit mass, per unit of mass. So it's not the total angular momentum, it's angular momentum per unit mass. And this all ends up being dimensionless. The other important point to capture is the fact that we chose G equals C equals 1 does not really have anything to do with dimensionlessness in the sense that we've just implemented. You can always do this in any unit system, and these coefficients here will always conspire ultimately to be dimensionless as long as you force one side of this equation to be dimensionless. You'll just end up with G's and 2M's or whatever unit system. You'll end up with essentially, let me quickly see, you'll end up with like a C squared here. I think you'll have a C squared here too. You'll end up with some C squareds if you choose G equals not C equals 1, and the A will be, I think you'll end up with 2M squared, and then you'll have a G, you'll have a 2M squared, and you probably have a G squared down below. Let me think. But what I'll do is later I'll actually write this equation in different units just to for my own amusement, if nothing else, just to get it all square in different units. But the point is that dimensionlessness in this context is unrelated to the dimensionlessness that we used to establish our unit system, which really isn't dimensionless, right? Our unit system's not dimensionless just because G equals C equals 1. The unit system still has centimeters, right? This is still in units, some unit of length, right? This is some unit of length. Kappa is truly dimensionless, however, but there are still dimensions floating around. The point is the independent and the dependent variable, those two are dimensionless. That's what we mean by the dimensionless right now. And let me just make sure I get rid of that little speck over here so it doesn't look like this row is anything but just a lone row star. Now we could change the form of this equation into this form, right? We could simply say, well, look, this is a fourth order polynomial with no constant term. So I can factor out a row star, and I can find, I'll be left with a cubic behind, and I can presume that that cubic has solutions, real and complex. In fact, it's got either, so it has solutions. So I'll call those solutions row 1, row 2, and row 3. And I'll just assume I know what those solutions are, and I'll write it in this form, and then there'll be some constant A out in front, which depends on the intricate nature of that cubic polynomial. So this form exists in principle, where everything could in principle be calculated. I could solve that cubic, figure out what A is, figure out the 3 roots, write it in that form, and that's another version of the radius anomaly equation, where the roots play a central role. Of course, this is a hard form because you have to solve a cubic, but that is always possible to do. It is always possible to find the roots of a cubic. In fact, it's not only always possible, it's always possible to do so through a formula. So this is considered simple, right? This is considered simple. It'll be a pain in the butt to do, and we'll probably be trying it a little later, but it is in principle simple. So that's another form of the radius anomaly equation. Also, you could say, well, wait a minute, what about this square here, right? I can just get rid of that, couldn't I? So here it is. I get rid of the square, and what do? I put a big square root over here. Well, that's another form of the radius anomaly equation where you don't have a square over here. It's kind of a trivial adjustment, but, you know, we already don't immediately know how to solve this, so it's not totally clear that that's much harder. But anyway, that's another way of attacking the equation. The other thing you can do is take the reciprocal of the whole thing, right? We could take the reciprocal of this, right, and write the following thing. Let me move everything up. So I shrunk it down a little bit, but I take this guy, right? I erase this, and then I write like that. Oops, wait a minute. I don't want to do that with this one. I want to just do it with this one. Well, it doesn't really matter. It doesn't really matter. That divided by, so now I write d phi d rho squared equals 1 over that thing, right? And I could then get rid of the square, and I could put a square root down here, like that, or I could set it equal to 1 over the square root of a times the square root of rho star minus rho 1, rho star minus rho 2, rho star minus rho 3. Now, the reason I'm going through all of this is there's a method of solving this equation for each of these circumstances, each of these arrangements. It can be done in each way. So, and also when you go through different books or papers, especially the ones I cite when I studied this, the ones I cited the most in the book I wrote called Why Does It Move? Different authors use different approaches, and it was kind of interesting to resolve each one. So I kind of go through all the approaches in parallel. That's sort of my method. And it makes us more familiar with the equations and a little more facile with them. But we're going to go back and use the basic form we landed on. So we're going back to this basic form, and our approach to simplifying this, our first approach to get at the function we're after, which is the answer to this differential equation, which is the radius anomaly formula, we're going to make the following substitution. I'm going to substitute chi equals rho star to the minus 1. Right? Chi equals rho star to the minus 1. This dimensionless Schwarzschild radius to the minus 1, or equals 1 over rho star. And therefore d chi equals minus 1 over rho star squared d rho star. I'm going to make that substitution. And so when I do this on the left-hand side, I'm going to end up with d chi d phi quantity squared, and I'm going to have whoops, I screwed that up. Obviously I screwed that up. I had that backwards, didn't I? This is the expression I need. I need d chi is minus 1 over rho star squared d rho star, but d rho star is minus rho star squared d chi. So I make the substitution for d rho star, and I get 2 of these factors out in front, which is just rho star to the 4th power. Okay, so with that, then I make the rest of the substitutions on the right-hand side. Well, let's actually do it a little differently. Let's take the left-hand side of that, and put this in its place, right? Maybe I shrink it a little bit so it'll fit. Put this in its place, and now we can see, so this substitution is legit. I just made the substitution on the left-hand side. Now I divide through by rho star to the 4th, right? So this term will cancel. This term will end up with a minus 1, and this term will end up with a minus 2, and this term will end up with a minus 3. So I should get this with this canceled out here, right? I just divided by this factor of rho to the 4th, which was living here a moment ago. Right there it was, and see, and now it is gone. right? And now I'm left with this, where now my rows, stars are in the denominator, but of course we have our substitution. Chi is 1 over rho star, right? So this is ultimately going to equal alpha squared kappa minus 1 over h squared plus alpha squared over h squared chi, right, minus chi squared plus chi cubed. And then this is d chi d phi quantity squared. Okay, so we've made this substitution. Now this substitution is kind of familiar in your advanced electromagnetics class. This substitution was not uncommon. I can't remember the exact name of the problem, but this was a routine solution in a routine substitution, this reciprocal substitution. Now remember, what about the range of these things? I probably should point that out, right? Rho star was greater than 0, less than infinity. But what about 1 over rho star, right? The reciprocal of this. Well, it's it doesn't take too much thinking to understand that it's really essentially got the same range. It's just banging up against infinity as rho star is at 0, and chi is banging up against 0 as rho star is at infinity. So when chi is equal to something like 0, you are at an infinite distance from the center. When chi is infinite, you're very, very close to the center as chi gets unboundedly large. Okay, so now I will write it in. Now we'll clean everything up a little bit by making sure our leading coefficient, our leading term is the largest power. Alpha squared over h squared chi plus alpha squared. This is our constant term, which is still dimensionless, over h squared. So this now is our favorite form of this expression, because now we have it in sort of cube, square, and notice that it's now a cubic equation, by the way. It's a cubic equation, and it has to do with the way that substitution was handled. It's now a cubic equation. So what's our last step? Well, we've got these constants here that we don't want to be carrying around, because remember, we're looking for the cleanest possible mathematical form. So we're going to sort of substitute away those constants. Okay, so from here on out, we're just going to be working on taking this equation and putting it into a few different forms. There's nothing very profound about what we're going to do to finish off this lecture, but we are going to take it step by step, just to see the different forms that different people, different researchers have used. The researcher that I'm following for a lot of this is a paper by a guy named Kostek, and I'll write in the comment section of this lecture the actual paper. But in 2012, Kostek wrote a really, really great paper about this, which basically sparked my interest in this, and I've literally duplicated his work in the book Why Does It Move? And that's what we're going to kind of do here. We're going to take it quite a long way through his work and the work of a few other researchers as well. But starting from this, we want to continue to work toward getting it dimensionless. And you might say, well, wait a minute, it's already dimensionless. This guy here is, we know that chi is 1 over rho star, and rho star is dimensionless, so chi is dimensionless, and then this angle is dimensionless, so this thing's already dimensionless. And it's true, right? I mean, if the left-hand side's dimensionless, then the right-hand side's dimensionless. That makes perfect sense. But these constants here, these ratios are dimensionless, but the constants aren't. So when we say something is totally dimensionless, we not only mean that the dependent and independent variables are dimensionless, but also all their factors are dimensionless too. Well, okay, so this factor is dimensionless, but we don't want any dimensionful quantities at all, even if they're dividing out to be dimensionless. So we want to get rid of them all. So we're going to define a new variable, s, which is, s is going to be equal to, well, let's see, wait a minute. We're going to do 4s squared is going to equal alpha squared over h squared. And that may seem a little weird, but s will be a dimensionless constant, so that's, at least we've accomplished that. Where this 4 comes from and why it works this way, that requires us to kind of go back and unpeel these things. H is simple. H, we know, was the constant of the motion associated with our initial analysis. So H is sort of this angular momentum per unit mass variable. So H is pretty easy to understand. Alpha, where did our alpha come from? Well, alpha came from the metric, right? It came from the metric. And we were given the metric as a given in this problem. So we never really derived what alpha was. It is the Schwarzschild radius of the gravitating body. But we never went through the process of figuring out exactly how to understand alpha. So we ended up with how did we get it? We got it as ds squared is 1 minus alpha over rho dx0 squared. That part of the metric, that's where alpha kind of showed up. It showed up in another part of the metric, but let's just imagine it also, plus the rest of the metric. The point is it shows up as part of the components of the metric tensor as expressed in the line element, right? That's how we were handed alpha. Had we derived this metric from scratch, which we will do eventually, we would have come up with alpha is 2gm over c squared over c squared. Now in our units, this would have been if we had done it in a fully unitful fashion. So in our units, this is just 2m, right? So alpha, so how would this work? So if we had made that substitution, then this coefficient here, right? This coefficient here is alpha squared over h squared, this guy, right? If we just make that substitution, we would have, let me do some erasing here. This would become 2m over h, 2m over h quantity squared, which is 4m over h squared. So s actually equals m over h, right? So s equals the ratio of the gravitational, this capital M is the only constant that really describes our gravitational field at all. And H has a lot to do with the initial conditions of the falling body. So S is a ratio of sort of the gravitational strength to the angular momentum of the falling body. So S is kind of a nice little ratio to have. It's dimensionless, which is good. So it turns out that this 4 seems to be a little superfluous to this nice ratio, so we pull it out. So we're going to end up with this 4s squared. Now, look, we could have just said, hey, let's just call this thing, let's just call it s, right? And then substitute it into the equation as s. We could have done that. But there is some insight to be gained by having this ratio floating around. Ultimately, when we do the analysis, finish up the solutions, we'll see s pop up in a way that's intuitive if we remember that s is this interesting ratio between the strength of the gravity of the problem and the initial angular momentum. So we're going to make this substitution. So let me take this stuff and just sort of move it aside in case we need it again. I don't think we will. And then this substitution will be, I have something else to say, I have something else to say about these constants, but it's chi cubed minus chi squared. Notice how you have nice things. This is very, the goal here is to trim this down into some really clean expression, and that 4 doesn't really help too much, does it? But kappa squared minus 1. I think I forgot the square on the last slide before this analysis. I think I lost that square at the very end there. Okay, so now this becomes our new expression, which is, you know, it's not a totally trivial change. But look, what do we got? We got we've got the square of a derivative is this cubic equation in the dependent variable. And the solution to this, as I'll always remind you, the solution will be some function of the inverse, this is some function of the inverse dimensionless Schwarzschild radius, that is 1 over rho star, which is alpha over rho, essentially, right? As a function of the true anomaly. That is what our solution will look like. So this solution will give us some path in space, right? And it won't inform us anything about how fast we're moving on it, because it's only two spatial variables with respect to one another. So what have we gotten? We've taken these constants and we've kind of squeezed them into S. Now let's understand what is happening here. You know, presumably we have a situation, it's spherically symmetric, so we have some mass that's going to be representing our star or our black hole or any gravitating body. And presumably we have some object out there that's our test mass. Now, in normal physics, normal Newtonian physics, our classical mechanics, we say, okay, we've got this body, it's got some initial velocity vector, so it's got some velocity in addition, where I'm using vector in the classical mechanics sense, and it's got some initial position, x mu, right? And that defines the problem. That's the initial conditions of the problem. Now, because it's spherically symmetric, this x mu can be, all it has to do is be specified as an r, right? Because any place around it is going to be immaterial. So x mu boils down to the number r, and this is just some initial velocity. Well, it turns out, and it shouldn't be, you know, as we also know from classical mechanics, this can be completely gobbled up into two different initial conditions, which is the initial angular momentum and the initial energy, right? In classical mechanics, the angular momentum and the energy of the initial particle will capture everything you need, given the fact that you don't particularly need this distance or this. You don't need to know where about the star you are. And that captures everything. You may not think it does, but imagine, so there's two circumstances, right? You can imagine a very, very, very fast particle that comes very, very close to the mass, right? Well, because of its speed, it has a high angular momentum, right? So the energy is high because it has a high speed. The angular momentum, in principle, should be low because it's passing very close to the center of the mass. But so this circumstance really captures both the how far away and the direction it's traveling in and the speed. It's captured by these two variables. The equivalent situation is you might have the same angular velocity, but a much higher impact parameter is the word I'm looking for. But kappa will be very low, right? Because you have it'll be much slower, but have a higher impact parameter. So different combinations of H and kappa will capture all the different possibilities there. And this can be turned into S. S and kappa will also capture the same thing, right? S now actually has the mass of the star brought into it, but S and kappa will also capture the same initial conditions as H and kappa, which will capture the same initial conditions as V and X. The difference between S and kappa is that S actually absorbs a little bit of information about the gravitational field itself, which if we just had this information here, we would have to use a form of the differential equation, that has A in it, has the Schwarzschild radius in it. That is where the strength of the gravitational field flows in, right, through this A. But if we then take our initial condition h and divide it by a, we end up with s, and now it's sort of absorbed in this single dimensionless constant. So all of these different ways are how you capture the initial conditions. The initial conditions are still part of the problem, these classic initial conditions, but they're buried in this form. You can't even say they're buried, because this is a legitimate statement of the initial conditions. We could argue that the initial position, or radial position, and velocity is buried in these initial conditions, right? You could go either way. Okay, so this is what we have now, but this actually can end up looking two different ways. Caustic has another form, which I'll write down. Here's a form that caustic uses. This is superficially a purely superficial change, right? A ends up being equal to 4. Let me see. A is 4s squared kappa squared, and B is minus 4. Let's see, s squared, I think. And you can it's just an algebraic conversion to this, but what's nice is now, of course, you have no square on the left-hand side. What's not nice is that now all of a sudden you don't have this nice pure cubic. You know, it's nice to have this cubic. Well, I guess there's a couple things that are not nice. One, first is this radical, and this plus or minus over the radical, and then inside the radical you have broken up this cubic into something else. But this is a form of the differential equation that's informative for its various reasons. I don't think we're going to study this form very much, but I just want to show you all the different forms that these kind of things can go in depending on how interested you are in different elements of the problem or different presentations of the problem. And then A and B can be interpreted in their own ways. But the form that we almost certainly will be working with in the next couple lessons is actually kind of an obvious, it's so obvious it's actually absurd, because what we're going to do is we're going to factor this. Just assume the factorization of that thing. I mean, remember, this is a number. You're given you initial conditions, you calculate that, that's a number, and that's a number. So this ends up being a cubic polynomial, which can be factored. It's not even, remember the quartic version, when we had rho, had an automatic factor of rho in every term. So, you know, rho equals 0 is always a solution, but that's not true here anymore, right? This is a pure cubic polynomial. Cubic, quartic, quadratic, linear, and constant term. So if I knew s and I knew kappa, I get a number, I take that thing, I solve it, I get 3 roots, right? So what do those 3 roots look like? Well, we'll call the first root u1, we'll call the second root u2, we'll call the third root u3, and there you have it. That's yet another form of this equation. And now all of the initial conditions are buried in this roots, which are the solutions of a cubic equation. So to get from these roots to this is actually, that's got to be really interesting. But of course, I think we actually will basically do that. I mean, these roots are going to tell us how this path moves. We're going to be able to solve. We're going to be able to solve for chi of phi the inverse of the dimensionless Schrodinger radius as a function of the true anomaly if we can integrate this expression, because we know how to solve a cubic equation, right? There's actually a formula to solve a cubic equation, so we know we can do that. So we know we can get these roots. Now you're saying, are you telling me that this is an impossible equation to solve? I mean, some mathematician probably in the 1800s has solved this equation, and it's true. But your regular calculus 2, right? Using your regular, I say calculus 2 because when I took calculus, it was the second semester when we studied integration. If I wanted to integrate this d phi, if I just threw an integral there, it would not, well, I say, hold on, let me get it right. If I just tried to integrate both sides, right, that would fail using calculus 2 methods, because you never actually learned how to integrate that in calculus 2. So we are going to have to take a diversion to learn how to do that integral. But there's still a lot to say about this equation. There's still a few more forms that it can be put into that are very useful to understand. And I think we'll begin the next lecture by starting from this point, right? We started this lecture, I guess, from this point. Or where did we start this lecture from? Let me think. We started this from the straight-up radius anomaly equation. Then we made all these substitutions, and we made the radius dimensionless by dividing through by the Schwarzschild radius, and then from that we made the conversion into this chi form, and then from that we dimensionlessnessed that by creating this S, and then we sort of factored it and created this guy. So we have really this equation here and this equation here to work with. Although, I mean, this is superficially different from this. But there's a few more forms that are worth understanding, and we'll talk about those next time.